In this section, we're going to talk about conservative vector fields. So a conservative vector field is just a vector field that is the gradient field of a potential function phi. So we're going back to what a gradient vector field is and what a potential function phi is. First, we're going to look at some vocabulary. We're going to look at the difference between a closed curve and a simple curve, and then we're going to look at regions. So when we talk about curves, we're usually looking at two-dimensional space. Regions, we're usually looking at three-dimensional space. In this top diagrams, there's four curves. This first curve is a closed simple curve. So closed just means that you start and end at the same point. And we talked about this in the previous section. Now this is a simple curve as well as closed because it doesn't intersect on itself. This next diagram is an example of a simple curve. It doesn't intersect on itself, but it's not closed. The ending and the starting points are different. Third example is closed but not simple. It's not simple because it intersects on itself, but it's closed because you have a starting point, and that's the same ending point. The last diagram is not closed and also not simple. It's not closed because starting ending points are different, and it's not simple because it intersects on itself. So for most of our discussion, what we want is we want the first example. We want to concern ourselves with closed and simple curves. Once in a while, we'll use a third example where it's closed and not simple is okay, but mostly closed, simple curves. Now the box below is just the definition of simple and closed curves, pretty much what we just talked about. When we talk about a simple curve, that means it doesn't intersect on itself, which means it's never going to be equal to itself. And then when we talk about closed, it just means that the starting point is equal to the ending point. The next thing we want to talk about is region. So a region is typically what we look at when we're looking at three-dimensional space. So when we talk about our regions, we're going to be concerned with connected and simply connected. If we look at these four diagrams, these are examples of connected, simply connected, or not connected, not simply connected. The first diagram, this region, this is connected. The reason why it's connected is because if I pick any 2 points, and it doesn't matter where these 2 points are in my region, I can connect them with a curve where the curve is also in the region. So it's simply connected. Oops. Simply connected means that if I pick any closed simple curve in the region, that I can collapse it down to a single point where that point is still in the region. So let's just say that I continued this and I keep doing that. Let's say I have this curve in my region, this closed simple curve. If I keep squishing this curve down and squishing this curve down, eventually I can get it to collapse to be a single point, where that single point is still in my region. So this region, this first example, is not only connected, it's simply connected. Now the second diagram, this diagram is connected. It's connected because if I pick any 2 points, and I'll just pick, why Storm? I'll just pick these 2 points that are on this curve. So if I pick any 2 points, I can connect the points with a curve that is still in the region. So the curve is in the region. This is not simply connected. Now it's not simply connected because if you look at this curve, this simple curve here, imagine collapsing that curve down to a single point. So making it go smaller and smaller and smaller. Eventually it'll collapse down to a point, but that point will no longer be in the region. So although it's connected, it's not simply connected. This third diagram is not connected, but it is simply connected. The reason why it's not connected is because I can pick 2 points in the region, and when I connect these 2 points, the curve that connects them is not in the region. Notice that part of this curve is outside of my region. Okay? So this is not connected because not all points can be connected by a curve where the curve is still in the region, but it is simply connected. If I think of any simple closed curve in our region, I can collapse it down to a single point where that point is still in the region. This last example is not connected, not simply connected. It's not connected because I can find 2 points where connecting them means the line that connects them is not in the region, and I can find a curve that will not collapse down to a single point that's still in the region. Okay. And now the regions that we're most often going to be concerned with is the first type, the connected and the simply connected. And that's what's in this box below, this definition of connected and simply connected regions. Connected, if it's possible to connect any 2 points by a continuous curve that's still lying in the region. Simply connected, if every closed simple curve can be deformed and contracted to a point in R. Something to note is in this definition it says an open region. So when they're saying open region, all they're saying is when you look at these regions, you don't have to consider that boundary, that black line. Okay? We're only really concerned with points inside the region, not points on the boundary of the region. Well, the next thing we're going to do is we're going to talk about conservative vector fields. So a vector field is conservative, and it can be on 2 or 3-dimensional space if there's going to exist a function phi, so we're going back to our potential function, such that the vector field is equal to the gradient vector field of phi. So let's say we do have some vector field and we want to test to see if that vector field is conservative. Well, let's just say the vector field is over a 3-dimensional region, so it's the vector field FGH. Then it's conservative if, when you take the partial derivative of f with respect to y, it's equal to the partial derivative of g with respect to x. The partial of f with respect to z is equal to the partial of h with respect to x. And finally, the partial derivative of g with respect to z is equal to the partial of h with respect to y. So this is on 3-dimensional space, so 3 conditions have to happen. But if you're in R2 or 2-dimensional space, you just have this single condition, and the partial of f with respect to y is equal to the partial of g with respect to x. So if the condition is met, then the vector field is conservative. What that means is this potential function phi, it exists. The first thing we want to do in example 1 is we're going to determine if our vector field is conservative. So what we're going to do is we're going to compute all those partial derivatives. Our vector field is negative 2x cosine y, so that would be our f. X squared sine y would be the g. And this is two dimension. So all we have to do is check to see that the partial derivative with respect to f, partial derivative of f with respect to y is equal to the partial derivative of g with respect to x. My partial derivatives look weird. So remember, the other way that we can write this is f sub y equal to g sub x. So what is the partial derivative of f with respect to y? Well, if we look at f, which is negative 2x cosine y, and we take the partial derivative with respect to y, it's going to be negative 2x times negative sine y, which turns into 2x sine y. Now let's take the partial derivative of g with respect to x. That would be 2x sine y. Ah, these are the same. So since their partial derivatives are equal, what we can conclude is our vector field is conservative. So again, what that means is there exists a potential function phi, so that f is the gradient vector field of phi. In example 2, we have this vector field, and this is three-dimensional space. We want to determine if it's conservative. So remember, I'm going to use a shorthand. It's the partial derivative of f with respect to y equal the partial derivative of g with respect to x. So we're checking to see that f with respect to y is equal to g with respect to x. And f with respect to z is equal to h with respect to x. G with respect to z is equal to h with respect to y. We have to check all three conditions. If it's true, then it's conservative. So what is f with respect to y? Again, this is f, g, h. With respect to y, that's simply negative 1. And then if you look at g and you take the partial derivative with respect to x, that's also negative 1. So first condition's met. What about f with respect to z? Derivative of e to the z is simply e to the z. H with respect to x is also e to the z. And then g with respect to z is 0. H with respect to y is also 0. So I can conclude that my vector field f is conservative. Okay, so let's say that our vector field is conservative. Again, that just means that there exists this function phi, so that f is the gradient vector field of phi. So how do we find our potential function phi? Well, you could go through this procedure, and there's 4 steps. Now, let's say that you can guess what the potential function is. That's fine. You can do it. You don't have to go through this procedure. Then again, there's 4 steps here. Let's say that you started to use this procedure and you went through step 1, step 2, and then you went, oh wait, I can see what the potential function is. That's fine. However, if you're going to guess what the potential function is, then you're going to have to check to verify. You don't have to go through all these steps though. So think about what this means. If you have a vector field FGH and you want to find the potential function phi, so that f is equal to the gradient of phi. Think about what that means. F is FGH. That means it's going to be equal to the gradient vector field of phi. So the gradient vector field is the partial derivative of phi with respect to x. Partial derivative of phi with respect to y. Partial derivative of phi with respect to z. So what we're saying is f is equal to partial derivative of phi with respect to x. G is equal to the partial derivative of phi with respect to y. H is equal to the partial derivative of phi with respect to z. The steps are, look at the first, in order for these guys to be equal to each other, oh, I've got this double comma that's going to irritate me. So in order for these guys to be equal to each other, they have to be equal to each other component-wise. So f has to be equal to the partial of phi with respect to x. Now remember, we're trying to find phi. So what we could do is we could set them equal to each other, set the partial derivative of phi with respect to x equal to f. That would be the first step. So to find phi, what you're going to do is integrate both sides of this equal sign. So when you integrate a derivative, you get back to phi. But remember, when you integrate, you're going to have a constant, right? And in this case, this constant could be a function of y and z. Because we integrated with respect to x, we still have 2 other variables. We have y and z. So again, the constant is not necessarily just a number. It could be a function of y and z. So the next step, step 2, would be to find that constant, figure out what it is. Well, what you could do is take this possible phi function that you got in step 1 and compute the partial derivative of that phi function with respect to y. That has to be equal to the g component. So if you set these two equal to each other, you should be able to find an expression for that constant, partial derivative of that constant with respect to y. Now this is all just blah, blah, blah. So at this point, if you haven't guessed what your potential function could be, then you would go to step 3. So these steps are integrate, differentiate, and you just keep doing that until you find your function. So next you're going to, because we have the partial derivative of our constant with respect to y, so you're going to integrate that. Again, we're integrating that constant that we found in part 2. So if we integrate with respect to y, then we'll get this constant. Plus, since we're integrating, we'll get another arbitrary constant. And this constant may be a function with respect to z. It cannot be a function with respect to x because we got rid of x on the first step. It cannot be a function with respect to y because we did that second step. So this third step where we integrate, or we did it on the third step, Once we've integrated with respect to y, then our next arbitrary constant is just a function of z. So the fourth step is that you would find the partial derivative of that function phi that we've been adding constants to in steps 2 and 3. Take the derivative with respect to z, set it equal to h, and then finally you can solve for dz. Now in this particular procedure, they started with taking f equal to partial of phi with respect to x, but you really don't have to start with x. You can start with any of those, g, h, and so on. So again, that's a lot of words. Let's see how we would find our function. In example 3, we want to find our potential function for this conservative vector field f. So we know this vector field is conservative. This is the same vector field that we did in example 1. We've already shown it's conservative. So we know that there exists this function phi, so that the gradient of phi is equal to f, which means that the partial with respect to x has to be negative 2x cosine y, and the partial derivative with respect to y of our phi has to be the x squared sine y. These guys have to be equal. Remember, this is our f, this is our g. So the first thing we want to do is we want to look at phi of x equaling f. So phi of x, partial derivative with respect to x, is equal to negative 2x cosine of y. But we don't want the partial derivative of phi, we want phi. So what we're going to do is we're going to integrate both sides with respect to x. Now once we do that, on the left-hand side, when you integrate the derivative, it cancels and you just get your function phi, which is what we wanted. Now on the right-hand side, if we integrate with respect to x, remember the negative 2 cosine y we treated as if it were a constant, so the x is going to be x squared over 2. The 2's will cancel, and I'll have a negative x squared cosine of y plus some constant. But remember, since I integrated with respect to x, my constant may not be a number, it may be a function of y. It cannot have an x and x I've already integrated with respect to x. Now this is just two-dimensional space. At this point, what we want to do is we want to find this constant. Now you could probably guess what the constant is, but if you don't, then you would go into the next step. So the next step says that we're going to take this phi function that we got in step 1, and we're going to take the partial derivative with respect to y. So remember, it's negative x squared cosine y plus a constant with respect to y. So the partial with respect to y would be negative x squared negative sine y, which is going to be a positive x squared sine y, plus, when I take the partial derivative of this constant with respect to y, since it could be a function of y, it's going to be c sub y, the partial derivative of this constant with respect to y. All right. So now what we're going to do is we're going to equate this partial derivative with respect to y with our g. So remember, g is equal to x squared sine y. So in order for these guys to be equal, that tells me that this constant has to be equal to 0. Otherwise, the partial with respect to y and g would not be equal to 0. So since I know the partial derivative of the constant with respect to y is 0, then I'm going to guess that my function phi with respect to the variables x and y is equal to negative x squared cosine of y. Because remember, what we're doing is we were trying to find this constant, and we're looking at this possible function phi. So if that constant is 0, then maybe my function is negative x squared cosine y. So I can check this. I can check this by looking at this potential function and computing the partial derivative with respect to x. When we compute the partial derivative with respect to x, we get negative 2x cosine y. Which is what we wanted, right? That's equal to that f. When we compute the partial derivative with respect to y, it's going to be negative x squared negative sine y, or x squared sine y. And that's equal to the g component of my vector field. So it checks out, and this is my potential function. Again, we didn't have to go through all those steps. It's kind of this weird integral derivative thing back and forth. If you could have guessed by looking at your vector field and thinking, okay, well, negative 2x cosine y, that has to be the partial derivative with respect to x. So you could mentally integrate with respect to x and probably guess what it should be. But those would be the steps. In example 4, it says find a potential function for the conservative vector field. And this vector field was the same vector field from example 2. We've already verified that it's conservative, so we know that this potential function p exists. How would we find that? Well, we could just look at our vector field and guess. Remember what this means. This means that the gradient of phi is equal to the partial derivative of phi with respect to x, y, and z. If I integrate the first component e to the z minus y with respect to x, then that should be my phi. So if I integrate with respect to x, it should be x e to the z minus xy. So let's say phi of x, y, z. Integrate the first component with respect to x. It's x e to the z minus xy. And I'm going to leave off the constant. So remember the second component, e to the y minus x, that should be equal to the partial derivative of phi with respect to y. So if I integrate that second component with respect to y, I will get e to the y minus xy. Well, xy minus xy is already listed, but e to the y is not. I don't have that in my potential function, so I'm going to add e to the y. So now let's look at our third component, x e to the z. That has to be equal to the partial derivative of phi with respect to z. So if I integrate with respect to z, I get x e to the z, which is already listed in my possible potential function phi. So if I were to just check this, the partial derivative with respect to x is going to be 0, negative y, oh, I'm sorry, e to the z minus y? Yeah. And the partial derivative with respect to y is going to be 0 minus x plus e to the y, or e to the y minus x. The partial derivative with respect to z is going to be x e to the z. And that checks out. Oops, partial derivative with respect to z. That checks out. That's my vector field F. So this is my potential function. Or, let's go back through the procedure. First, take the partial of x, you set it equal to f, which is e to the z minus y. And then you integrate both sides with respect to x, which is kind of what I did mentally in that first step. So again, you can always guess and check, or you can go through this procedure. On the left, it becomes my potential function with respect to x, y, z. And on the right, when I integrate with respect to x, I get x e to the z minus xy plus a constant, and this constant can be a function of y and z. So the next step is to find this constant so I can solve for my potential function. Well, the next thing I'm going to do is I'm going to take that potential function and I'm going to find the partial derivative with respect to y. Looking at that first component, x e to the z, partial with respect to y, it's 0. The next component would be a negative x plus the constant, take the derivative with respect to y, and it could be some partial derivative written in terms of y and z. So I'm going to take that partial derivative with respect to y, set it equal to the g component, or compare it to the g component of my vector field F, and that g component was e to the y minus x. So when I compare these two, what that tells me is they both have a negative x, so it must be true that the partial derivative of the constant with respect to y is equal to e to the y. So now what I'm going to do with that equation is I'm going to integrate this constant with respect to y. So integrate both sides with respect to y. On the left-hand side, you integrate the derivative, you get back to the constant with respect to y and z equal to, on the right-hand side, that's e to the y, plus this new constant. But since I've integrated with respect to x and now I'm integrating with respect to y, This new constant we'll call d, can only be a function of z. So now this is what I want to find. So let's look at what our function phi looks like, phi looks like so far. So far we have x e to the z minus xy plus e to the y, we're putting all this together, plus dz. As remember, we already solved for c, so now we're solving for d. I'm going to take this potential function and now take the partial with respect to z, which would give me x e to the z minus 0 plus 0 plus partial d with respect to z. So I'm going to compare that to h, which is x e to the z. And the only way that these two can be equal is if the partial of d with respect to z is equal to 0. But that doesn't mean that the constant is equal to 0. But you could probably see that it is. What it means is if I take the integral with respect to z, it's equal to the integral of 0 with respect to z. So integrating on both sides, we get that d of z is equal to 0. And that tells me that my potential function is equal to x e to the z minus xy plus e to the y, which I found by sort of doing some educated guessing. So at any time, if you could see what the potential function is without going through these steps, that's fine. Just guess, but don't forget to check by taking the partial derivatives. And then you can also go through the procedure. You don't have to go through all 4 steps. I just went through all 4 steps, but you don't have to. You could go through 1 or 2 or 3, and you could stop at any time when you see what the function is. So now what we're going to do is we're going to look at theorem 16.4, which is our fundamental theorem for line integrals. So this corresponds with the fundamental theorem of calculus, but it's applied to line integrals. So let's say that we have this vector field f. Oops. And let's say that we have our potential function so that f is equal to the gradient vector field of phi. So f is conservative. So if f is conservative, then what that means is that our line integral, which here's the 2 forms of our line integral, can be computed by using the fundamental theorem of calculus, but it's applied to line integrals. So we can take this potential function that we found, and we can just look at phi of b minus phi of a, which is the fundamental theorem, but applied to a line integral instead of just the general fundamental theorem of calculus. In example 5, we're going to use this. So in example 5, it says evaluate the line integral for this function phi, which is x times y. And we have this oriented curve, cosine of t, sine of t. So that curve would be a circle. T values from 0 to 2 pi, so it's a closed circle, and it's connected, simple. It's oriented. It's got all the nice stuff going on. We're going to do this in 2 ways. We're going to first compute our line integral doing what we did before. We're going to use the parametric description with the parameter t, and then we're going to do it by using this theorem. Okay, so let's first look at doing this the way we did before by looking at a parametric equation. I have my function phi, and I know that it's a potential function. So when I compute its gradient vector field, which would be the partial with respect to x, that's just y, partial with respect to y is x. I know that's going to be equal to some vector field f. So that's what I'm going to put in my integral. And now remember, in this middle form, this dr, so this dr is equal to r prime of t dt. Ugh, that looks terrible. I gotta erase it, it's gonna bug me. So remember, the differential of r is shorthand for r prime of t dt. So going back to my parametric representation, I can go ahead and take the integral of my vector field dotted with the derivative of r with respect to t. That's the integral from 0 to 2 pi. My vector field is yx. So y is sine of t in my curve r. X is cosine of t. So y comma x would be sine cosine. The derivative of r is going to be negative sine, positive cosine. So it looks like when I do my dot product, I'm going to have negative sine squared plus cosine squared of t. Okay, so there's a variety of ways that I could integrate this. I could split it up into two integrals and I'll have a sine, sine, cosine, cosine. Don't know if that'll help me at all. Another thing you could do is go back to your trig identities. So cosine squared minus sine squared is actually cosine of 2t. So I think that's what I'm going to use. As I can easily integrate that into sine of 2t over 2. And then evaluate that from 0 to 2 pi. So sine of 4 pi is 0, sine of 0 is 0. This just becomes 0. So remember, this was a line integral. It ended up to be 0. Remember, line integrals are also work integrals. They're also circulation integrals. So there was 0 work, 0 circulation if this was an application. So let's go back to using this theorem. And we have our function phi, which is equal to xy. So remember, our curve is x is the cosine, y is sine. So I can write phi as cosine of t times sine of t. And I want it to be written in terms of t because this fundamental theorem says that my a and b have to be written in terms of t. Everything's in terms of t. So what is this b and this a? Well, those are our limits of integration. Our t values go from 0 to 2 pi, so 0 is the a value, 2 pi is the b value. So all I have to do to evaluate this integral is compute cosine of t sine of t, where I'm going 2 pi to 0. And that's the fundamental theorem. So this is cosine of 2 pi sine of 2 pi minus cosine of 0 sine of 0. And that's simply 0, which I expected we would get because we did it the long way from our previous sections, and we got 0. So this theorem just gives you another way that you can compute line integrals, as long as you know you have this potential function phi. Okay, last theorem in this section is theorem 16.5. This is looking at our line integrals on closed curves. So let's say that we have this region, and it could be in 2 or 3-dimensional space. It's some open region. Then let's say F is a conservative vector field. That means that when you compute your line integral, the line integral is going to equal 0. In our last example, we computed our line integral and we got 0. That means that our vector field is conservative, which we knew it was because we had this potential function phi. Anyway, look at this new notation. Look at our integral symbol. It has this word circle in there. Well, when you see the integral symbol and it's got this circle stands for this closed curve. So all that is shorthand for saying we're going to integrate over this closed curve. So you may see that in your physics classes. In example 6, we want to evaluate this. We evaluate the integral over this vector field xy, where C is the circle of radius 4 centered at the origin, and it's oriented clockwise. So our curve can be written parametrically as it's a circle radius 4 centered at the origin. So we could write this as 4, but we have to be careful because it's oriented clockwise, not counterclockwise. So usually our circles go counterclockwise and it's a cosine sign. So if you wanted to change the direction, one way we could do that is to exchange sine and cosine and write this as 4 sine, 4 cosine. And that would change the direction from counterclockwise to clockwise. Another way we could change the direction is keep it as 4 cosine, 4 sine, but replace t with negative t. So that's another thing we could do. And I'm going to go from 0 to 2 pi because it's the whole circle and it's closed. So I have to start and end where I began. This would be my x and my y. So the derivative is equal to 4 cosine negative 4 sine. And my integral over the closed curve from 0 to 2 pi. And if you're given an integral with that circle on it, you should continue to write it that way, is the vector field xy dotted with the derivative for cosine t negative 4 sine t dt. So the last thing I need to do is to replace x and y so everything can be written in terms of t. I have my integral for sine t, for cosine t, dotted with 4 cosine t, negative 4 sine t. Okay, this is going to be 16 sine cosine minus 16 sine cosine. Which is simply the integral of 0, and that's equal to 0. So I computed this line integral, I got 0, which is great. What does that mean? Well, what that means by this theorem is that my vector field F is conservative. But what this last theorem gives us is it gives us another way to determine if a vector field is conservative. So if the vector field is conservative, when you figure out this line integral, it's going to be equal to 0. Okay, so anytime your line integral is equal to 0, your vector field is conservative. And that's it for this section.